My name is Anton Rodriguez. I am Principal Software Engineer in Relic, working mostly with the data platform team and helping to evolve our data platform. And with me today is Ramesh.
Hello, everyone. Thank you for attending our talk. I am Ramesh Mottapurthy, Principal Software Engineer at New Relic. And what excites me the most about working at New Relic is the scale at which it operates. And what drives our scale is our architecture. And Anton is going to talk about our cellular architecture, some of its benefits, and some of the challenges. And then later in the session, I'll be deep diving into one of the solutions that we are coming up with to solve one of the challenges. So, Anton?
Yeah, our talk is basically about two things we want to share. One is the cell architecture and how we implement it in New Relic. And another one is how we are combining Kafka and object storage, like S3, to address some of the issues or the challenges we have with the cell architecture. So let's start first with New Relic. In case you are not familiar with this company, New Relic provides monitoring observability capabilities for other companies. So basically, the idea is other companies are running things like OpenTelemetry collector, like agents, like Prometheus, basically sources of data, of telemetry data, to know the status of their systems, and they send all that data to us, to New Relic. In New Relic, we process that data in near real time. We store that data in the New Relic database, and then we have a set of capabilities on top of it to understand what's happening with the systems, how to optimize it, how to optimize them. Things like proper alerting, dashboarding, optimization, understand the relation of the different systems between themselves, and that type of things. The interesting thing about New Relic is, or one of the main reasons because I joined New Relic in the first place, is the huge amount of data we manage every second. So those numbers are not up to date at all, but they give you an understanding of how much data we process every second. And this is only for ingestion. There are more use cases in New Relic. We have more infrastructure for other things in New Relic. But just for ingestion, it's very clear for us. We cannot run things with a single Kafka cluster because we cannot keep adding more brokers to it. We need multiple Kafka clusters. We need to be able to scale our data streaming infrastructure in order to be able to grow and to accept more data from our customers. And that's the first thing we want to share here today, is how we implemented the cell architecture 3 years ago to address this particular problem. So if you're not familiar with the cell architecture, let's start with a short introduction to the different components of it. The first one is what we call a cell. So for us, a cell is just a unit of a specific workload. I'm going to use ingestion as an example first. And all our ingestion cells, they are basically the same thing. They have a Kafka cluster. They have a Kubernetes cluster, all together deployed as a unit in AWS or Google Cloud or Azure, in a cloud provider account, and with their own network, their own VPC. So the thing about the cell is it has all the resources we need to process telemetry data, and it's contained, and we can have multiple cells, and all of them have the same configuration, the same components. So all of them have Kafka, all of them have the same topics with the same number of partitions, the same number of brokers, the same services consuming or producing into them. So basically, they are I like to see them as mini data centers with all the things we need, and we can easily create or eliminate them when required. Now, having multiple cells is how we can scale, but that also forces us to have another component to decide how we send the traffic from our customers, the data from our customers, into the cells themselves. And that is the cell router. Cell router is, we can see it as a smart load balancer, which is able to understand what cells are available and how it should route specific measures to a specific cell. And it also be able to react to changes in the topology of the cells or the status of them. If a cell is not healthy for whatever reason, the cell router is able to detect those situations and to react to them in real time. And finally, the last component we have is the control plane. Now, when we were running in the data center with a very small number of Kafka clusters and infrastructure was pretty easy, but now we are running hundreds of brokers, hundreds of Kafka clusters, all of them should have the same configuration. And that means we cannot go and make a manual change in one Kafka cluster or in all of them, because it just takes so long to go to every resource to make the change. So in general, making manual changes to infrastructure is never a good idea. But with the cell architecture, it's just not a bad idea. It's not possible. It will take too much time for us. So we need a control plane able to manage all that complexity, all those resources, and to deliver the changes to them as a unit. So let's go with a more clear example of the cell architecture in Relic. And the first one for me is ingestion. So here we have all those things from our customers sending data into the ingestion shell router, which is basically a CDN able to query our cells and to understand where are deployed and what's the status of them, and then decide to what cell are sending the data coming from a specific customer. And it sends the data to the cells themselves. We process the data there, and we send the data into New Relic DB later. Now, if the traffic in our in Relic, or the traffic our customers are sending to us grows a lot, the only thing we need to do is to add more cells to be able to keep ingesting that traffic. If one of the cells is having a problem, what the ingestion cell router has to do is just stop sending data to that cell and send that data to others. So that gives us a lot of better reliability in general for our customers. And here we have a bit of a view of the benefits of the cell architecture. In the picture, we can see the migration from the monolith, from the data center, into the cell architecture. We were able to migrate everything from the data center into the cloud in 1 year for ingestion. And we can also see how we were able to ingest a lot more traffic embracing the cell architecture. So that's the first thing. The second one is, if one cell is having issues, the other cells shouldn't be impacted because they are not sharing any resource, any common infrastructure. And that also allows us to isolate cloud issues. So not all our customers are impacted by them, just a small set of them. And it also allows us to just move traffic away from cells having issues, so our customers are not impacted. And finally, one of the main benefits of the cell architecture is because now we are working with cells and they have very defined configuration, it's much easier for us to work in optimization of those cells because we understand how much traffic we send to them, what type of use case we have, and we can optimize Kafka and Kubernetes and all those resources specifically for those use cases. And we can test that in one cell, see the benefit of the changes, and if we see those benefits, then we can apply that change to all the other cells and keep improving the platform in that way. Now, the cell architecture also has a lot of benefits, but it also introduces complexity and some challenges. I already spoke about the control plane and how we need a very good and solid control plane to manage all the cells. But another challenge we have is how to move or how to replicate data between cells. And the thing is, now in the cloud, we have multiple different cell types. Right, we have, for example, in this case, a cell type for ingestion, but we have also a cell type for alerting. So alerting is a cell type which is receiving data from the ingestion cells, and it's evaluating that data in real time to generate alerts. Now, that workload is very different, and the optimizations we want to do for Kafka, for Kubernetes, for the applications, it's also different, and we want to scale that workload independently of ingestion. So it makes sense for us to have a specific cell type only for alerting, but it also forces us to have a component able to consume from the ingestion cells from all those Kafka clusters and send that data into the alerting cell type. And that's the Kafka cell router, right? And this Kafka cell router is pretty complex. It's not like Mirror Maker or Replicator or other technologies able to move data between Kafka clusters, because it needs to consume from a huge amount of Kafka clusters in the source. It needs to send that data into the Kafka clusters in the destination. And it needs to understand how our cells are deployed and what's the status of those cells in every moment. So if we add new cells, if we decommission cells, the Kafka router needs to understand those situations and needs to react to them in real time. And finally, this component, it also needs to enforce isolation between cells. So if a cell is having problems, it needs to react to that and to make sure other cells are not affected because of that. Now, we have last year, Julia, one of our colleagues, did a talk here in Current, which is recorded, speaking about this component in detail, all the things we were doing with it, how we were trying to improve it, and some of the problems we have with it, right? The summary of that talk is because we are using Kafka under the hood in the router because we want to have back pressure and we want to be able to route those messages in a smart way to different cells. This component, it's pretty complex, it's pretty expensive, and introduces latency and reliability issues in our pipelines. So something we have been exploring internally for the last year is how to embrace object storage, and in particular, the ability of doing streaming over storage and combining it with Kafka to try to improve and to solve some of the architecture challenges of this particular component. So Ramesh is going to tell us how he has been exploring that pattern of streaming over S3 to be able to improve that component and improve our cell architecture thanks to it. Ramesh.
Thank you, Anton. So just to recap the use case, this use case is the routing use case where you are basically trying to take events from one cell and then distribute them to one or more target cells. So, and we will be using Apache Flink for this as our streaming runtime engine. And as Anton mentioned, we'll be using object storage, which could be S3 or any S3 compliant storage like MinIO. So this is our simplified architecture diagram, the new architecture diagram. As you can see, S3 takes the central stage in this architecture. In S3, you will be having different partitions where each partition could be mapped to one target cell. So what will happen is that, so in this picture, you're seeing like 3 source cells on the left side and 2 target cells on the right side. But in reality, you will be seeing like tens of hundreds of these cells where we are routing the traffic to and from via S3. So on the source cell, you'll have a Flink job running, which we call it as the Kafka to S3 job. So the primary responsibility of that is to stream events from Kafka, figure out where these events need to go to, which target cell they need to go to, and then stream it to S3. And then on the target side, you have a similar job running, which is S3 to Kafka job. Basically, what it's doing is streaming any new events that are coming to S3 and streaming back to the target Kafka topic. So that's the simplified architecture. As you can see, the source cells are no longer connected to the target cells. Everything is flowing via S3, and if the target cell is up or down, it doesn't matter. Source cell will continuously keep writing its data to S3. And this reduces a lot of complexity, especially with respect to networking. All these source cells, they are basically in different AWS accounts, and you don't have to set up any VPC pairing or any kind of networking setup to communicate. So everything is happening with S3. But what we are saying here is S3 can be used as a message source. So you might be asking, S3 is a file system, sort of a file system. It's a name value, key value store. But how could that be a message store? So let's take a look at some of the options we have to basically expose S3 as a message store. So the first option we have is Apache Iceberg. It is an open table format. The open here means open source. And table format is basically a specification that tells you how to organize your data files in large distributed file systems like S3. And it's all about metadata management. So they let you create metadata which you'll use for high-speed analytical processing. So Iceberg, it is open sourced by Netflix. They are the maintainers. It was released in 2017 and then open sourced in 2018. And it is one of the most popular open table formats out there, which is used for running large analytical queries on your data in the data lake. So, but in our streaming use case, we really don't care about the analytics. We are not going to run any queries or anything like that. What we are interested in is streaming. So basically, Iceberg also exposes a streaming API. It's called incremental scan. So any consumer of the Iceberg table, it can run this incremental scan, figure out what events are being pushed into the table, and then it can stream those events out. So this is the capability that we are interested in for this use case, and all the options that we'll be looking at will be looking at from the streaming perspective and not from the analytics perspective. So the next option we have is Apache Paimon. Apache Paimon is also an open table format, but the project originated from within Flink as a Flink table store. That's what it used to be called, but then they made it a standalone project later so that they could support other engines as well. And the authors of the Paimon open table format, they took inspiration from Iceberg. This came into existence after Iceberg, after several years of Iceberg. So their focus was mainly on the low latency and the streaming use cases. And this exactly fits our use case as well. We want to stream the events as soon as possible with the lowest latency possible. So that's the second option. And the third option is to basically keep it simple. Following the KISS principle of the software engineering, we don't want to use any table format in this case. Just use S3 as a regular file system. As soon as you have new events coming from the source Kafka side, you create files, push them into S3, and you have a monitoring process on S3 that is monitoring and getting all the new files and streaming out to the target Kafka clusters. So that is another option. It's a very simple option, and we looked at that as well. So let's take a look at our journey, how we evaluated all of these. That bar right there, that is our timeline. And the first thing that we evaluated was Apache Paimon. So we had the jobs up and running within a couple of weeks for the POC, proof of concept project. And we had the New Relic dashboards up and running so that we can monitor all the metrics about the Flink jobs, how they're performing, and Apache Paimon stats as well. So one thing that we liked about Paimon was the consumer tracking feature. So it's very similar to what Kafka does with its consumer groups support. Any consumer of the Apache Paimon, they can start, when it starts the job, you can add a consumer ID. So what Paimon does is it will keep a bookmark, basically a place in the table where you are at while you are reading the table data. And for any reason, if the job restarts, the consumer is able to go back to that bookmark and start exactly from that point. So that is very good for us, which means that we don't have to rely on Flink's state. So whenever you upgrade your jobs, you can start with the clean state, and Paimon will remember where exactly we are and start streaming from there. So Paimon is designed for low latency, and they did deliver on that based on the metrics we saw in our jobs. So we ran through a bunch of throughputs, basically all the way from 10,000 messages per second to 1 million messages per second. And for all these tests, it was always under 13 seconds, 5 to 13 seconds. On an average, it was taking 8 seconds. So the latency is actually comparable. This is where we were really surprised. The latency is comparable to what we had originally with Kafka being the message queue. And the latency here is not, it's the end-to-end latency, which includes the latencies all the way starting from your source cell and then your routing layer, which determines like where each of these events needs to go to, and all the way transmitting to the target cell. So that was a good thing. The third thing that we found with Paimon was that it had some difficulty streaming large amounts of data. So this is a case where your consumer might go down for an hour or so, and then you have so much of data accumulated in S3. When the consumer restarts, that's when it was having some problems, where the job was restarting. So this is when we reached out to the community for help, and we also tried to reach out to the Apache Paimon authors. And while this was happening, we tried Apache Iceberg as well. So again, we deployed the jobs in a couple of days, and then stood up the jobs dashboards to compare the new Relic dashboards with Apache Paimon. And one good thing that we found with Iceberg is that it was using less number of S3 requests. So AWS charges you based on the number of requests that you make into S3, not necessarily the size of each request. So Iceberg was somehow optimizing the number of requests for to support the same amount of throughput. So that was a positive thing going on for Iceberg. But we did notice that as the throughput increased, the latency increased as well. So when we went from 10,000 messages, the latency was about 6 seconds, which is very low, which is good. But as we went all the way to 1 million messages per second, the latency went up almost to 33 seconds or so, which was not ideal in our case. So that was the kind of a blocker for us because we have to support a very high throughput of millions of messages per second. So the next, and on top of that, it did not provide the consumer tracking feature for us. So in the meantime, the Paimon authors, they did set up a meeting with us, and then we had a positive outcome from that. They did help us solve that problem that I mentioned before, and we were all confident with Paimon at that time. And so up until now, we were deploying the jobs in only one cell. But as Anton mentioned, we have hundreds of cells. So we need to deploy these jobs, these Paimon Flink jobs, on multiple cells. So that's what we started next. And as soon as we deployed these jobs in other cells, these concurrent jobs, they started competing with each other. So basically, Paimon supports atomic updates to the Paimon table. And when we added new concurrent writers to that table, that's when things started failing. The jobs were restarting. And this is a known problem. And the solution for that is to implement some kind of distributed locking so that these writers can take turns when updating the table. But as soon as we did that, the latency increased back to like 30 seconds to 40 seconds. So that was not acceptable. And one of the other important attributes that we need in our jobs is scaling. We want the jobs to auto-scale. In cellular architecture, the throughput can vary a lot. So when there is a problem with one cell, the throughput, the traffic will be routed to a different cell. So you can expect like double the throughput within minutes sometimes. So we wanted scaling to be very elastic, and that was not the case with Paimon. And retention is also very important in any option that is streaming over S3, because if you don't take care of retention, you're basically increasing your latency every day. And also the compute usage, because every 5 seconds, all these jobs are writing a bunch of files into S3. And your writers and readers, they need to parse through all these files to figure out which ones are the new ones so that they could stream. And retention was a bit difficult to implement with Paimon. It was also expensive. Retention is a process where the Paimon runs on a scheduled basis. What it's doing is it's figuring out all the expired partitions and then deleting all those files. So basically, this retention job itself was competing with the writers and the readers. And that was slowing down things, and it also was expensive because it was taking a lot of S3 requests. So the next thing that left for us to try was the last option, which was the file sync and the file source option. And I'll explain in more detail what this option is, but some of the benefits that we found with this were that it was using the minimal resource usage, basically. If the Paimon and Iceberg were using 20% CPU, this was using 5% CPU usage. So that was one good thing going on. And it supported unlimited scaling. So you could go all the way to like 512 subtasks, and it was able to auto-scale at that level. So that was good. And retention was very easy because in this model, we are not storing any of the references or anything like that, like the way that they store the metadata in Iceberg and Paimon. So as long as you know that you have consumed a file, you are able to just delete that directory, and then that takes care of it. So one thing that we did find, which was a negative for this approach, was the higher S3 cost. It was making more number of S3 requests. Basically, the file source operator that constantly monitors the files to figure out like which ones are the new files, that was taking using a lot of S3 requests, which increased the cost. So we are actively working on this one, and we hope that we can bring the cost down to what Iceberg is doing. So that's the approach that we are going with right now. So this is how our Kafka to S3 job looks like. So we have 3 operators, main operators. The first one is the Kafka source, which is basically reading your events. This is the job that is on the source cells. So it is taking the events from Kafka source topic and then deserializing them into objects that the job is using. All these objects then flow into the route function. The route function is the one that's responsible for figuring out the destination cell for each of these events. So the output of this route function is an enhanced object that has this cell name, the destination cell name. So all these events then flow into the file sync operator, which is the file Flink's native operator. And the file sync operator uses a bucketing mechanism to bucket based on the destination cell name. And every 5 seconds, it buffers all the data and then rolls out new files and then pushes them into S3. So that is the streaming model. So on the right, you're seeing the view that you will see from Flink UI. You can see that all of those 3 operators have been combined into one operator. And Flink calls it operator chaining. This is done for efficiency reasons. So when you do operator chaining, the efficiency gains are because you don't have to serialize and deserialize all these events that are flowing through each of these operators. So that's where we'll be saving a lot of compute usage. So that's our source job. Now let's take a look at the target job. So this is the job that lives in the destination cells. So we are using the file source operator. Again, it's provided by Flink. It's a native operator, but we had to do a lot of customizations on top of that. So this is monitoring every 2 seconds. It's monitoring the S3 directories, figuring out which ones are the new files, and then it outputs. It basically reads all the Parquet files and then streams the records out of the file source operator. All those events then flow into Kafka sync, which is responsible for pushing the events back into the target Kafka topic. And on the right, you can see the job graph as seen in the Flink UI. Again, this is a very highly optimized job. So yeah, that's about our jobs. Now let's take a look at some of our learnings. We learned some of these the hard way. We hope that they'll be useful for you. So the first learning is that when evaluating streaming over S3 options, don't forget retention, give retention the importance that it deserves, because retention is very, very important in any of these options. If you don't run retention regularly, then you're basically increasing your latency and increasing the compute usage as well. And in each of these options, retention is a bit different. Some options it is very easy, some options it is very tough. So you have to consider retention when evaluating all these options. With Paimon, we did find a lot of difficulty implementing retention to keep the job stable. Yeah. So the next one is to avoid small files. Anytime you're streaming over S3, try to avoid small files. In some cases, it's not possible. And the way that Apache Paimon and Iceberg deal with this problem is by running a process called compaction. So what compaction does is it takes a bunch of small files and then merges them together to make bigger files, larger files. And that's what creates the efficiency. But again, that compaction process needs to be run regularly, and then it also consumes compute, obviously. But there are a few ways where you can that you can use in Flink to avoid small files. This is possible only in some cases. So yeah, it depends on the use case that you have. One is partitioning. Partitioning is where you are dividing your data into different buckets so that you can query the data easily. So if you have to query on, let's say, a particular destination cell name, you can just go to that partition, look at the files inside that partition. So, but if you do over partitioning, then basically you are creating a lot of small files. So you have this big stream of data coming in from Kafka, and then let's say you have 10 partitions. That big stream of data should now be distributed among 10 partitions. And every 5 seconds, you are creating 10 files instead of one file. So if you can avoid partitioning, avoid it. That's the learning. And very similar to that, we have parallelism. The recommendation is that go with the minimum parallelism that can support your throughput. So basically what this means is that for a given throughput, a parallelism of 2 is much more efficient than a parallelism of 10, because if you have a parallelism of 2 for the same exact throughput, you have 2 subtasks that are working on the stream of data. Every 5 seconds, they are creating 2 files into S3. But if your parallelism is 10, let's say, because you want to handle higher throughputs in the future or whatever, let's say you go with a minimum parallelism of 10, then you are creating 10 files, smaller files, because the throughput is the same. So the recommendation is to go with the minimum parallelism that is possible, that supports your throughput. Ideally, your parallelism should be elastic. It should just move up and down depending on your throughput. That is the ideal scenario. And the next one is the buffering time. So as I mentioned before, we use 5 seconds as our buffering time. So every 5 seconds, we collect all the events, roll them into files, and then push them to S3. But if we were to increase that 5 seconds to 10 seconds, then you're basically creating larger files, which will increase the efficiency. But at the same time, then you are sacrificing on the latency. You're basically doubling your latency. So if you have if you can tolerate a bigger latency, then go with that setting for the buffering time. So I just simplified it in Flink. It's called checkpointing. Yep. So the last learning that we have is this. It's an observation. A job that is running a particular throughput, if you increase the throughput, the cost is not going to go much higher. Again, the reason is because S3 is charging you based on the number of requests you are making into S3, not by the size of each request. So a higher throughput job is basically creating bigger, larger files, but making the same number of S3 requests. So if possible, have jobs that are handling higher throughputs. In some cases, it's not possible because maybe your throughput of the topic itself is very low, right? So in those cases, what you could do is handle multiple topics. The same job, instead of handling one topic, can handle multiple low throughput topics. The downside is that your data will be co-located inside the files, but that's fine in some use cases. At the target level, you can split the files again and then push it to the target Kafka topics. So that's my last learning. I hope these are useful to you guys. And with that, I'll give it back to Anton.
Well, just some final thoughts to kind of summarize the talk and the key insights for us. The first one is how we are now combining Kafka and S3 for streaming, and how we are using those capabilities to improve our architecture and to simplify it. And some of the things we have been learning for the last 6 months is streaming over S3, it's possible. It's kind of a trade-off between latency and cost. But in some use cases, makes our life much easier than Kafka. Not for others, but in some situations, because it's always is highly available. How we connect to it is different in the cloud, and for the cross availabilities on charges and things like that. In some situations, doing streaming over S3 is just much easier. So we see a lot of potential in this pattern of combining S3 object storage with Kafka for streaming, but we also see a lot of complexity happening, and we felt like early adopters of that pattern in many situations. Flink has been very helpful for us because it provides this abstraction layer where we can switch from Kafka to S3 to other things if we want using Flink. So it gives us a lot of functionalities out of the box to connect to S3. So Flink is for sure something which is helping us a lot in that journey. And finally, what's next for us is we think we are going to keep using this pattern of combining S3 and Kafka. For sure, we are going to keep working with it for the routing use case and evolving in that direction because we are already seeing benefits on that. And we are also starting to use it for other use cases inside New Relic. A very common use case we have in New Relic is to retrieve data from databases and store that data in Kafka in compacted topics. So our Flink jobs or other streaming services can connect to the compacted topic to retrieve the data instead of having to go to the database. This is a pretty common pattern out there. Now, the problem with that pattern and the cell architecture is we end replicating those topics everywhere, and that's very redundant. We have the same data coming from databases in many different places, and it's pretty expensive. So some of the things we are already working on is let's replace those compacted topics, which are everywhere, in a single S3 bucket, and let the services connect to it and receive the updates from it instead of having it through Kafka and all that mirroring we need to have in place between databases and Kafka. So that's another project which is also using this new pattern of streaming over S3 to simplify a lot of things in terms of architecture and also cloud cost. That's all. Thank you for your time for being here today.